Hello, my name is Kristine, and I'm a postdoc at DTU Wind Energy. And I will talk about some initial work we've done with some computational studies, trying to test out some different types of particles for anti-erosion coatings. And this work is done in collaboration with Gediminas from Kaunas University of Technology and Leon from DTU Wind Energy. So do we look into why is leading edge erosion a problem? You probably already know this, but wind turbine blades, they have to operate under various weather conditions, such as heavy rain and winds, and they still have to last for like 20 to 30 years. And now with them getting bigger and bigger and also being in harsher and harsher environments, we have even more issues, and they're very high tip rotation speeds. They can even go up to close to 100 meters per second. So you can imagine some big block of material just going with 100 meters per second into these water droplets. They might not feel so soft anymore. And what happens is that we have wear on the mainly the leading edge of the wind turbine blades, and this is this rain erosion. So for example, I've included just an example here where you can see some severe case, but it is really a problem that we have to do something about. So this is where this project DuralEdge is working on developing new erosion resistant coatings, and that is the project that I've been working on now for the past 5 months. So this project has a total of 6 work packages. I'm not going to go into details with this, but I'm part of the second one, which is focusing on this computational modeling part. But of course, they are highly interconnected, or they have to be to give some good results. And just to give you an idea of this, I'll just mention some of the many focus areas that we have and that I have been touching upon a little bit these past 5 months. So we need to have an understanding of the material properties. Many of these coatings have, for example, polyurethane, which is quite hyperelastic and also viscoelastic. So you need some complex material models. Need to understand the damage mechanisms as well, especially also to be able to make a realistic model. You need to know what is going on to some extent. We need to understand liquid impacts as well, which is quite difficult to model actually. Some of my colleagues and previous colleagues has already done a lot of very nice work on this. I have included some references here. But we also need to understand the influence of different filler particles in these coatings. And all of these things you need to combine into some multi-scale model scheme that then can also be used later on to do some lifetime prediction. We already have some lifetime prediction tools developed also by a previous colleague, but of course there's still work to do. And then also combining all this, we want to develop these new coatings that should be able to last, well, hopefully the full life of the wind turbine blade. So for my talk this time, of course I have to focus somewhere. So I've been working on this part for the past recent time. So trying to understand some of the effect of these filler particles, and then hopefully be able to give a little bit of input knowledge for the people trying to do experimental trials. So why is this necessary? Well, we want to develop a new erosion resistant coating, but if we just go completely experimental, and we have so many possible variations of many different things, such as, well, we have different types of resin. So we might have PU, but there's also different types of PU and many different things you can try there. Different filler particles, you can have different numbers and combination of layers of coating on top of each other, and also different layer thicknesses, and there's probably much more that is possible to change here. But it would simply take too long time to test it all. So we have to make some choices on what to choose to focus on. And for good or bad, previous know-how and experience can give some biased results. You can say that you don't go in a direction that might have been good because it didn't show good results once before or something like this. So we're hoping that we can use modeling to, of course, reduce the number of cases to be tested experimentally, but also to reveal new possible improvement combinations that we might not have imagined would be good. Yes. So first, let's talk about a little bit about what can make coatings erosion resistance. And we've made two main hypotheses in this study that we've been working on based on literature reviews and so on. And one is that scattering of stress waves can improve the erosion resistance. And the reason I've called it hypothesis is that it's not 100% proven, but quite well documented to some extent, you can say. So this could be scattering on particles. So maybe, for example, here you have some disk where you can see the stress wave move down and then reflected away from the original direction, or well, some other types of particles. We can also have some reflection of interfaces. This has been proven to give better erosion resistance, having more layers. So aside from this, we also have another hypothesis that we believe that we can have a network of fibers in a resin, so as fillers, that can then improve the damping properties by, you can say, the entangled structure of these fibers. So that's the theory. So that we believe that we have the coating properties that are governed by, of course, by the resin-induced damping properties. So, for example, the viscoelastic properties, but also by these filler-induced damping properties. So even if we have elastic fibers, then the combination of this viscoelastic resin and this somehow entangled network of fibers, that this can somehow also improve the damping properties. And we might also have something with the interfaces. But in the current work, we've focused on these two, so scattering on particles and looking a little bit on the filler-induced damping properties. So yeah, so just want to show what a droplet impact looks like if in a model using some HPH to model the water droplets. So it's some particle modeling technique. Where you can see here in the video, this is the droplet going down to the surface and splashing out. And then I've just removed all the low stresses, so it only shows the higher stresses moving. But what you can see is that if you just look at one point here, the stresses are really changing depending on what time you look. And of course, such effect would have to be included in a model. But for this initial study, we've chosen to focus on taking a simpler approach to begin with. So what we've assumed is that we have this material point below the droplet. And then when we look at a sufficiently small unit cell here, then we can assume that it's a homogeneous impact on the top of this unit cell. And the reason that it makes sense for the purpose of this study is that we want to compare the effect of different types of filler materials. So we're not going to predict the lifetime with this exact model. That will be later on, hopefully. But we want to compare the mechanisms for these different types of fillers. So we've looked at these different types of fillers. So 4 volume% of small discs. And we have 1 volume%, 4 and 8 volume% of curved fibers. And it's trying to simulate some kind of pulp structure where the fibers are kind of entangled in some way. And this has been generated by the Digimat software. So let's take a look at the first hypothesis with the scattering of the stress waves. So we've just made this small model here where by impacting here on this surface, like this. So this is pure PU. You can see the stress wave is moving from the top to the bottom here, and we're only looking at the first stress wave, so moving like this. It's assumed there's symmetry boundary conditions on the other surfaces here. So comparing different cases, we can see here this figure shows the exact same time step for different cases. In these 3 models, we have hidden the stresses that are below, I think it's around 2 megapascal, just to show, make it easier to see the particles as well. But well, you can see that the stress wave here is moving relatively far down, quite fast in the pure PU. In the well, in the 4 volume percent disk case and also the 4 volume percent fiber case, the stress wave is moving actually quite similar, but there are some points where it seems these long fibers are leading the high stresses further down into the materials faster, you can say. Now, if we look at 8 volume percent of fibers, we can really see that the stresses are scattered or led much more fast through the volume. So just to look a little bit on this, it's easier to see it in videos. If you look at the 4 volume percent fibers, just the stress wave moving down, it is scattering the fibers, but it's moving relatively straight down. Now, if we look at the 8 volume percent fibers now over here, we can see that it's getting scattered to a larger extent, you can say. It's a little bit difficult to see, but you can see that the stresses are really moving around here. So, so we have, it seems we have higher scattering for the higher volume percentage, which might make sense also logically. Okay, so taking a look at the second hypothesis about the damping induced by the fibers. So what we've done now is to try to apply an impact load on this again. Now I've turned it around just to make it confusing. But so what we've done is just impacting this block and then looking at it bounce up and down, and then tracking the average displacement of this whole surface, and then plotting this kind of displacement versus time. So if we get inspired a little bit by vibrations theory, we can say that the damping of the system maybe can be estimated by how fast this is going down, you can say, into not moving. So if we do this for pure PU here and compare it to different volume fractions of curved fibers, that's what we've done here. We can see that the pure PU is the blue curve, and then the 1 and 4 volume percent of fibers is a little bit, it seems to go a little bit faster down here, but it's not that different. And also 1 and 4% are quite similar to each other, more than I would have thought. But when we go to the 8%, we really see a big difference in this behavior. And this is probably not only due to damping, I'll get back to that, but some of it is probably, I think. So let's look a little bit more into details with the mechanisms of this 8 volume percent case. So this shows only the high stresses, again, hidden all the lower stresses just to make it easier to visualize this in 3 dimensions for this 8 volume percent case. So it's a video where we can see we push it down and release, and then we have stresses in between the fibers, but they start actually focusing a little bit in the corners. And just to make it a little bit easier to see, this shows this top surface displacement of this 8 volume percentage of the fiber case. And if we look at this point, we can see that we have some stresses that are high in between the fibers. They're building up here in between where the fibers are close to each other. And then when we go to the second top peak here, we can see that we have some stresses starting to focus a little bit in this corner. And now if we go even further, we have quite a lot in the corners as well. So, but if we look at a point further out here, we can also see that the stresses, they have relaxed eventually, which we also would expect. So what does this mean? Okay, so this shows the viscous dissipated energy extracted from Abacus, which is used for these finite elements simulations per unit volume for the PU, the polyurethane, and the 8 volume percent fiber case. And if we look where this nicely uniform deformation time step of the unit cell, it's around here. So we still have a difference in viscous dissipated energy between the PU and this fiber case. But if we look up here where there's a very big difference, you can see that the aerosols is probably the big difference, at least, is because of this effect we have in the corners that it's bouncing. But I would say that looking at the images, at least here, that it only starts bouncing diagonally from around this point, and we can still see that there is a difference in the viscous dissipated energy for these cases. But of course, it should be looked more into detail, and it could be fixed by considering a larger volume, so it won't bounce so locally like this, and maybe also periodic boundary conditions. Okay, so to conclude and like make a note on what we can use this for in the experimental work. So we have found that the presence of particles, they scatter the stresses, and that is more pronounced for higher volume percentage of the fibers or particles. So we've also found that the presence of fibers dissipate more viscous energy, which is also more pronounced for higher volume percentage. Of course, this additional viscous dissipated energy in these highly stressed regions, it can also lead to crack initiation points if there are weak interfaces or defects. But we believe that if we have a highly interconnected network of pulp, that it could potentially work as also crack progression stoppers. So it might be a combination of these things that could actually make a good coating, a part of a coating. But we are working on this and also need further experimental trials, of course, and more expanded models to confirm confirm this in detail. So that was what I had to say. I just want to acknowledge Drill Edge and my co-workers working with me there for working with me and telling me a lot of stuff about this project, and thanking you for your attention. So thank you.